Welcome back to the channel, everyone. So today I have picked up a problem from center of mass chapter, and it's from one of the past FIITJEE AITS papers, and the question looks like a bit lengthy and a bit complex, but trust me, it's a easy one once you proceed the first or second steps. So the problem states that a part of the surface of hemisphere is isolated from hemisphere by cutting it by two planes passing through the same diameter and forming an angle with each other. The shape thus obtained is called a mericap. The left part is referred as mericap with central angle alpha. They're saying that these shapes are called mericaps. Many of you must know already. So these kind of shapes are mericaps, right? And if this is cut from a solid sphere or solid hemisphere, this is a solid mericap. And if it is cut from a hemispherical shell, a hollow sphere, then it is called a hollow mericap. Find the distance of center of mass of a uniform solid mericap of radius r equals to 16 by pi and central angle alpha equals to 10 degree from the center of the sphere, and we are given an approximation that for angles less than 7 degrees we may assume sine theta is equals to theta. So basically we are given the r, alpha and everything values. So we'll put those values later on. We'll just first solve for generalized case, and we are asked to find about the distance of center of mass of a uniform hollow mericap of this radius and this central angle from the center of the sphere. Let's say this mericap is having center of mass somewhere here, and from center distance is r. So we're interested in finding out the r. Obviously it will depend on capital R and alpha, so we'll put those values and get our required result, right? So let's get started. So first, if this side is making an angle alpha, or this is a mericap of angle alpha, I'll define this side as a mericap of angle pi minus alpha, right? Let's say this is the horizontal line. Now let's say this is the left part, this is the right part, and mass of left part or the left mericap I am defining at ml, and mass of right mericap I am defining as mr. So from proportionality we can write ml upon mr is equals to alpha upon pi minus alpha, because obviously as this central angle, the angle made by the cutting plane with the horizontal will change, the volume of the mericap will change, and subsequently its mass will also change. So obviously it will be proportional to the angle subtended. More the angle subtended by these two planes, horizontal plane and the cutting plane, more will be its mass. And as it is a homogeneous sphere, so mass distribution is uniform, so we can claim that the left side mass or the left mericap mass and the right mericap's mass, the ratio of mass ratio will be equals to the angle ratios, the angle subtended by the cutting plane and the horizontal. Here it is alpha upon pi minus alpha. So that is our claim. So let's say we are writing ml, the left part mass, as k alpha, and m right as k times pi minus alpha. Obviously k is a constant. So what we'll do, that for a mericap, let's say this is a mericap of angle alpha, this angle is alpha, or wait, sorry, this is a kind of mericap, and yeah, this is the line and this angle is alpha. So what you can do is, we're not sure that at what distance the center of mass of this part is from the center. Obviously this is the center of the sphere or hemisphere, but one thing for sure, that as the mass distribution is uniform, let's say this is the mericap, the center of mass will lie on the angle bisector of angle alpha. That much you can definitely say, somewhere here the center of mass will lie, but this distance is still not known to us, and this is our purpose. This is our target. We will find the RL value only. RL I am denoting just for the left part, and I will write RR as the right part. Okay, so this was my first claim, that the center of mass will lie on the angle bisector of angle alpha, as this is a uniform mass distribution case, so center of mass will definitely lie on this line due to symmetry. And the same logic goes for the right hand side medicap as well, that we will claim for this medicap somewhere here the center of mass will lie. This line is the angle bisector of pi minus alpha angle, right? So let me erase a few terms and proceed to the next one. Yeah, so I'm not drawing the medicaps again. I'll just show that here the center of mass of the left part is lying. Let's say this is RL, and this angle will be definitely alpha by 2, because the whole angle was alpha and this angle is the angle bisector of alpha. And from this side you can tell that center of mass of right hand side will be somewhere here. Let's say this is R of R, the right hand side. This angle will be half of pi minus alpha, pi by 2 minus alpha by 2. And interestingly, if you join these two medicaps, finally it will give an solid hemisphere, right? And for solid hemisphere, the center of mass is known to us. That's a very general, frequently we use the result of the center of mass height from the base in case of a solid hemisphere, that is 3r upon 8, and in case of hollow hemisphere it's r by 2, right? So this is a very general result and you should keep it remembered, right? And so I'm marking here as, let's say, CM combined. I'm defining like this, because if you join these two medicaps, it will finally convert into a solid hemisphere and center of mass will be here and its height will be 3r upon 8. So it's kind of a easy problem now, right? That you have two masses. Let's say this one is, we have already written the masses right here. This is K alpha and this mass is, let's say this is M1 and this is M2, or let's say ML and MR. Let's keep the notations same. This, so you just know the positions and the coordinates of two different masses and you are trying to find out the center of mass of the combined system. It's kind of a that problem now, right? So now we will just do with this position of center of mass of the combined in horizontal and vertical, I mean the x and y direction. I'll calculate from the two different bodies and will equate with the known result of 3r by 2, right? So it's clear that the x coordinate of CM of combined is 0. Let me define this as x-axis and this one as y-axis. So xCM of combined is definitely 0. So from here we can write that, let's say MR times its x coordinate. I'll write, right? So its x coordinate will be RR times cos pi by 2 minus alpha by 2. Right, this distance is R of R, and so this distance is the x coordinate of right hand side mass. So this will be R of R into cos of pi by 2 minus alpha by 2. Similarly, this will be equals to mass of left ML, which will be equals to RL cos of alpha by 2. Obviously the x coordinate is 0 combined system, so we'll just write m1 x1 equals to m2 x2 for two particle systems, right? Where x1 and x2 are the distances from center of mass to that particles. So let me put the values. I mean, let's say MR I am putting as K alpha and here is R of R. This will be sine alpha by 2, cos pi by 2 minus theta is sine theta. This will be, I've done a mistake here. MRR will be K times pi minus alpha, and this will be K times alpha RL cos alpha by 2. K gets cancelled and we have got RR in terms of RL. It will be like this, cot alpha by 2 R of RL. So this is one of our important equation. because this equation relates the RR and RL. We will require this relation later on. Let's see. So we are done with the x coordinate. Now we will proceed to y coordinate. For YCM combined is 3r by 8, as we have already seen. So we'll just equate this by calculating the YCM from two masses. It will be, for left mass, let's say for right mass, it will be k pi minus alpha mass. This one is the mass of right, times RR sine of pi by 2 minus alpha by 2, because this is the y coordinate, right? This is the y coordinate, r of r into sine pi by 2 minus alpha by 2, plus, now I am writing for left medicap, it will be k alpha, its mass, times RL sine alpha by 2 upon the total mass. Total mass will be k pi, obviously, because it's k alpha plus k pi minus alpha is k pi, or you can simply say that the total angle subtended here is pi and k was our proportionality constant, so total mass will be k pi. Okay, so this will give the center of mass of the combined system as 3r by 8. Now it's just a calculation, so k gets cancelled, and here we'll get pi minus alpha upon pi RR will be cos alpha by 2 plus alpha times RL sine alpha by 2 will be equals to 3R. Now we'll require the equation number 1, because we are trying to find out RL, right? Because for any medicap subtending an angle alpha, we'll claim that its center of mass will lie at a distance of RL from center, and that will be a generalized result. So we'll try to substitute R of R in terms of R of L. So from 1 we can write, this one was R of R, right? So pi minus alpha upon pi into alpha upon pi minus alpha times cot alpha by 2 RL into cos alpha by 2 plus alpha times RL sin alpha by 2 equals to 3R upon 8. Here pi minus alpha gets cancelled, and we'll get a alpha. So we'll get alpha upon pi RL. If we write cot alpha by 2 in terms of cos and sine, we will write cos square alpha by 2 upon sine alpha by 2 plus, oh wait, sorry, I have done a mistake here. This pi was in the denominator, right? So I have divided the first term with pi but forgot to divide the second term also with pi. So here will also be a 1 pi in denominator. Here will also be another pi. So let's do one thing. We just multiply the pi on the right hand side, right? So we'll get alpha RL sine alpha by 2 into 3R by 8 into pi. So if you take alpha times RL common, it will be cos square alpha by 2 plus sine square alpha by 2 upon sine alpha by 2 equals to 3 pi R upon 8. This will be 1 cos square theta plus sine square theta. So RL will be nothing but 3 pi R sine alpha by 2 upon 8 alpha. Okay, so this is actually a generalized result, I would say, but here we have given also another approximation, right? And that is valid only for angles less than 7 degree. Here's the approximation. For angles less than 7 degree, you may assume sine theta equals to theta. Here we are trying to find, let me write first that this is generalized result, and we are trying to find for R equals to 16 by pi and alpha equals to 10 degree. In this case, alpha by 2 is 5 degree, which is less than 7 degree. So we can write sine alpha by 2 as alpha by 2. So in this case, we'll get R let's say now I'm writing RCM because we're solving for a particular case. So RCM is 3 pi into 16 upon pi. Sin alpha by 2 we're writing as alpha by 2, and here it will be 8 alpha. So alpha alpha gets cancelled, 8 to 16 gets cancelled, pi pi gets cancelled. So R1 will be 3, and that will be answer. So this is the answer for our question, that the center of mass of this mericap, I mean the angle, the mericap which is obtaining an angle alpha, is at a distance of 3 units from the center of the sphere. And I think this was our question, right? Yeah, we are done with the question. So that's all for today, and thank you. Stay tuned for some more interesting problems.